We developed some strategies for solving systems of two linear equations. In other words, finding a value of y and a value of x, which will make both of a set of two equations true at the same time, simultaneously. On the first of these two problems, we found out that the method of substitution is actually a pretty quick and efficient way to get rid of one of the variables, get rid of the x's or get rid of the y's, because that's our ultimate goal, our ultimate strategy for how to solve a system of two equations and two variables, is to try and get us an equation that only has one variable in it that we can solve. And then once we solve that equation and find the value for that variable, we can plug it back in and find the value for the other. And for this first equation, first system of equations rather, because it's set up in a way where we explicitly know how y relates to x. In other words, the y in the first equation has already been solved for. It's by itself. That lets us fairly efficiently use the method of substitution to replace y in the second equation with the quantity 3x minus 4. And then at that point, the y's are all gone from the second equation, and we're off to the races. And so the method of substitution is really easy to use immediately in this first of these two problems that we looked at on Monday. The second problem, though, substitution was not as natural of a fit. In order to use substitution on this second system of equations, we first had to do some overhead. We had to do the work ourselves of getting one of the variables by itself. So when we did this at the end of class on Monday, we decided to take that second equation and solve that equation for x. And when we do that, we had to do a few steps of algebra. We get this nice fraction, negative 3/5 showing up here. We find out that x is equal to negative 3/5 times y, according to the second equation. And once that x is by itself, then we can use substitution to replace that x in the first equation by negative 3/5 y. And then from there, all the rest of our work was just wrapped up in getting that y by itself, solving for y, plugging it back into the system, and finding x. But the important feature I want to draw our attention to get us started today is that we'd like not to have to do this step here in order to get started with this system of equations. What we want is a method that doesn't require us to make a substitution, because not every system of equations that we solve is going to be set up for us to do a substitution quite so quickly. Let's take a moment and consider this system, this new system. 3x plus y equals 5, and 2x minus y is equal to 0. We could approach solving this system of equations graphically. We could graph the two equations, as is done over here on the right, and then look for that point where these two equations, where these two graphs intersect. And based on the graph, it looks like the solution of this system of equations is probably x equals 1, y equals 2. But again, graphs speak 1,000 words, but they sort of mumble. Right? We don't know exactly, just based on an eyeball of a graph, whether or not 1, 2 is the exact answer, or whether it's something close that's sort of masquerading as 1, 2 on the graph. So we want an algebraic method to find that solution. And we could approach this system using the same substitution method as the example that we just looked at. Solve one of these equations for one of the variables. Maybe I could rearrange this equation so it says y equals 2x, and then I could substitute 2x in for y and get 3x plus 2x equals 5. I've eliminated a variable, solve this equation, and get x equals 1, and then plug that 1 back into the system and find out that then y is equal to 2, and then we're done. So we could approach this using substitution, but that's not the point of what we're talking about today. The point is for us to find a new method of approach that some people like better, some people don't like as much. It's always going to be your purview to choose which of these two methods that you prefer. I'm never going to force you to use one or the other. But it is good to get practice using them both so you can make an informed choice on which one you like to stick with. So here's how today's method works. This is method 2. We call it the method of elimination. The method of elimination works not by looking at one or the other of these equations by itself, but rather by taking them both and combining them both together in one step. And the way that we'll do that, in general, the important step, is we're just going to add these two equations to one another. Add their left-hand sides together, add their right-hand sides together, and thereby discover a new equation. So if I add, for example, the right-hand sides of these two equations, I'll get another equation whose right-hand side is 5 plus 0, in other words, 5. If I add the left-hand sides of these two equations, I'm going to end up with, I'm going to write out all the brutal details here. 3x plus y plus 2x minus y is what I would get on the left-hand side if I just literally added the left-hand sides of these equations together. But what's kind of nice about that is that I can simplify this expression over here, because I have a couple of terms that have x's in them. What do I get when I add 3x plus 2x? I get 5x. Those are like terms. Right? They both have the variable factor x. And so when I add them, I combine the coefficients. By adding them, I get 5x. So that's what happens to my x's. What happens to my y's? They cancel out, because the coefficients on these y's are respectively 1 and negative 1. So when I add those like terms together, I end up with how many y's? I end up with 0 y's. And 0y, 0 times y, is the same thing as 0, because that's how 0 rolls. Right? 0 times anything is equal to 0. And also, 0 plus anything is an invisible operation. And so what adding these two equations together did is it accomplished that goal that we always have in solving a system, which is somehow get rid of a variable. In substitution, we got rid of a variable by substituting an expression. In elimination, we get rid of a variable by adding together two equations in such a way that that variable disappears, that its term cancels out. And now that we've achieved that, we're not done, but this is where we've reached the important step now that y has been eliminated. And all we have to do now is the same process as we did before when we were solving systems. Finish solving one equation, whereby I'm going to get x is equal to 1. And then take that value and back substitute it into either of the two original equations. Just because the second one seems a little bit simpler to work with, I'm going to use the second one. 2x minus y is equal to 0, but x now we know is equal to 1. And so I'll plug a 1 in there for x. And then 2 times 1 is 2. 2 minus y is equal to 0. I'm going to do kind of 2 steps in one here and discover that that means y equals 2. So sure enough, this method of elimination has provided for us the confirmation that the exact solution of this system is, in fact, x equals 1, y equals 2. And so the only difference between this method and substitution is in how we get rid of a variable. In substitution, we got rid of it by substituting. In elimination, we get rid of it by adding the equations together in a way that makes that variable cancel. And that was real easy in this example, because already, in the very beginning, one of my equations had a y, the other equation had a minus y, and when I added those two together, y was gone. So that's kind of nice, right? It feels like the algebra we had to do here was not quite as heavy of a lift as when we had to substitute, perhaps. Right? So elimination is kind of friendly. This example was set up really nicely that all we had to do was just add, and my y's vaporized. Let's look next at an example where we have to work a little bit harder than that.